So continuing with some design tools, we're looking here at routing algorithms. And routing algorithms are responsible for connecting the ports or the I/O of an already placed design together. It's usually accomplished in several phases. One phase will be the channel generation, so you have to define regions in which the connections will be routed. And typically the channels are rectangular regions, and non-rectangular regions often are partitioned into rectangular regions. So here's an example. You had defined connections. You know what the connections are after you've placed this. You know, that's, for example, E has to get down to B. And at this point in time, then channels are defined. Then you want to go to the process of, or step of global routing. So if a net has to be routed between two channels, a port basically is created on the boundary between the two channels. So this represents the port formation, because I know I had to go from this channel to this channel down here. So the channel through which a net is routed is determined during this step, and no actual connections are made. So there's nothing routed up or wired up in here, but the port connections are shown on the individual channels. So then the channels are actually routed, so the wires are placed so the connections are made. We'll see that in figure D coming up in a minute or two. Routing is a common procedure for all types of ASICs, ranging from full custom, standard cell, gate array, and field programmable devices. And routing, like placement, is a difficult problem, and since most routers will not find an optimal solution, it is important often that nets are prioritized so that perhaps you might meet timing constraints. So this would allow a critical net to be routed with the best efficiency, and maybe making other nets which aren't as critical routed with less efficiency. So here's an example of the channel routing that's taken place. It shows each of the channels routed up. And basically the in-class assignment here is what design philosophy exploited with global and channel routing. And hopefully it'll be apparent it's pretty much of a divide and conquer type of strategy. And there's the picture of the steps there. The interconnects are made, the ports are made, or the channels are made, the ports are made on the individual channels, and then the channels are routed. And so you can sort of see that even though it's a very simple problem, it's going to get relatively complex as you have lots of nets that you have to route. And here's this example of a simple Lee-Moore routing algorithm. It's very old, and really it's just to point out that other techniques might be useful at some point in time, and really this is just a breadth first search from a source to a destination, and it's sort of illustrated here. Sort of ran out of steam though with the colors. This would still be all those that are 3 hops away, sort of 4 hops away, 5, 6, 7, 8, 9, and you get a route from start to the finish, and you avoided areas that you weren't able to route on. So in class assignment 7.5, what graph search algorithm does that most closely look like? And a follow-on question might be, what type of compute paradigm might prove useful for this type of routing algorithm? And hopefully you'll be able to at least say something intelligent about the former, maybe a little less so about the latter. With respect to channel routing, again, often it's more convenient to route multiple lines at the same time, and that's an approach that's often taken by a channel router. You place parallel wires through the primary direction of the channel. Horizontal wires would route horizontally, and vertical wires would route vertically, and they would be on different metals of layer, so they wouldn't different levels of metal, so they wouldn't interfere with one another. And here's the example of a channel router where you have horizontal nets routing horizontally, and there's 4 nets in this figure, so there's 4 basically reserved areas for the horizontal wire, and then it would be connected up with the vertical wires. Certainly this is not the most efficient way to do this layout, but it's certainly one that could be implemented to try to constrain the complexity of these types of designs. So one of the questions that arose in class, if there are so many metal layers with modern technologies, why not just route over the cells as opposed to having routing channels? Well, that's a very good question. And for example, let's say you have metal 1 through metal 3. Those could be used within a cell. So typically you wouldn't be using those within over the cell, because you use in a cell, they'd interfere with them, of course. So the metal 2 and metal 3 would require routing channels. But metal layers 4 to 8 could conceivably route over the cell, and that's called OTC. That stands for over the cell. And there you'd have this detour around vias, which as required. Power grids and clocks may consume a couple of extra layers as well. So you have to account for the fact that you have to route the clock, and we looked at that very early on, and you certainly have to route lots of power around. And they also take up with their own metal layers, but certainly there seems to be a tendency to route over the cell. Here's a couple of pictures of training materials that I found online, and this clearly illustrate rows of cells represented by routing. So this would have been cells. So these are your logic blocks, or your combinational logic or sequential logic function. And in between here is a whole bunch of routing channels. This is just another picture zoomed in a little bit, but it clearly shows sort of some standard cell routing placement areas, and then some routing between the where the standard cells are not. Here's an example of a DSP. I forget what the chip is exactly, but you can sort of see that this is relatively modern, as I recall, and a lot more of the area went to the standard cells than the routing itself. And here's an example, maybe even zoomed in on the previous one, but it certainly still shows that you can certainly see the rows of standard cells, but most of the area is consumed by standard cells as opposed to the routing channels that we saw previously. So here's an example to put things in perspective again. This is our 2-input NAND gate. There was our transistor level schematic. There was our low level layout. And here it is sitting down here again, separated by power and ground rail. So this would be within a standard cell, placed somewhere, connected up, and that whole bunch of standard cells would be sitting somewhere in a chip down here, let's say, for example. So that just sort of illustrates we have a placement problem, followed by perhaps the creation of routing tracks within this particular design tool, some global routing, and then some detailed routing. So the summary for that question that came up in class, that appears as of 2012. Still some of the chips are routed with routing channels, but there does seem to be a transition to over-the-cell routing. It also appears that both global and detailed routing phases are still widely employed, and that'll bring us to a break time.